So in this video, we're going to talk about connected regions with holes. So if I have one hole in a region, then the boundary of that region will contain an outer boundary and inner boundary. I'm going to argue that if the outer boundary is counterclockwise and then the inner boundary is clockwise, I can divide this region into two regions without holes and then use the Green's theorem on those two regions to deduct a conclusion for the region with holes. So let's start with the region D, whose boundaries are these two, inner and outer, and then cut the region into two pieces by cutting through the hole. Now I will get these two regions. And in these two regions, I have one boundary that belongs to the outer boundary of the original region. Let's call that up. And then another boundary down here is the original lower part of the outer boundary. And then there's another piece here that is the inner boundary, up, inner. And then here is the up and down, inner. And then we have extra pieces. So the first region up there has this extra piece and this extra piece. And then the other region has that extra piece and this extra piece. When I write the line integral on the upper region, what I get is that over the up f dot dr, then over here is the C C1 west and C1, C2 west. So basically it's going to be over C1 east f dot dr and plus up inner f dot dr plus C2 east f dot dr. So this is the entire boundary. So this is the contour integral over region D1. So this is the contour integral over region D1. And this is by Green's theorem, because the region D1 doesn't have any holes, it's going to be equal to the double integral of the curl of f on this region, basically. You can do the same thing for f dot dr in the region 2, and what you get is you get the one on the down plus C2 west plus over here boundary down inner and plus the last piece is C1 westbound. The fun part is that C1 westbound and C2 westbound are going to add up to 0, eastbound and westbound. These two add up to 0. C2 and C2 east and C2 westbound, those two add up to 0. So if I add these two sides, these 4 are going to disappear, and then I will have upper boundary plus the lower boundary of the outer and inner together. So basically, the boundary D1 FDR plus boundary D2 F dot DR is going to be equal to boundary the outer boundary D F dot DR in the counterclockwise direction plus clockwise direction, and I'm changing that, inner boundary of that. So if I add all the boundary of the first one plus all the boundaries of the second one, the line integral on those, I'm just going to get the outer boundary clockwise, counterclockwise of the original, and plus the clockwise inner of the original. And remember, according to Green's theorem, the first one of these was double integral of a curl z direction dA on D1. The second one was the same thing on D2. So the sum of these two is going to add up also to the double integral on the region D of curl of F, z direction dA. So if you have a hole, basically adding the line integral of the outer bounds in a counterclockwise direction and inner bounds in the clockwise direction gives you the double integral of the over the region, shaded region.